Okay, so we have discussed a lot of stuff about orthogonality and orthogonal basis, but we didn't actually answer a fundamental question. How do we find an orthogonal basis? So in this section, we're going to find the answer for that. So we will get to know how to create an orthogonal basis for a subspace W of R to the n. And that procedure is called as Gram-Schmidt process. So first of all, suppose that W is given by span of x1 and x2, and x1 is given by this vector, and x2 is given by this vector. And we're going to find an orthogonal basis for W using these two vectors. So idea is the following. So basically, well, geometrically, if you have a space W, and you have two different vectors, like x1 and x2, then you begin with a single vector x1. So let's say this one equals to v1. And we can find the vector orthogonal to v1 by subtracting orthogonal projection of x2 onto x1. So let's say this small vector to be the projection of x2 onto v1. Then if you set v2 be x2 minus the projection of x2 onto v1, then we get two orthogonal vectors v1 and v2. So let us verify this idea by using this example. So first of all, we begin with a vector x1 equals to v1 that is given by 1, 1, 0 in this case. And let's say a w sub 1 equals to a span of v1. Then we can find v2 by subtracting orthogonal projection from x2. So x2 minus projection of x2 onto w1. And this gives you, well, x2 is given by 2, 2, 3 above. And the projection of x2 onto w1 is given by x2 dot product with v1 over v1 dot product with v1 times v1. Then this equals to 2, 2, 3 minus. So x2 dotted with v1 is, well, we have to take the dot product with these two vectors. So that gives you 2 plus 2 plus 0 over v1 dot v1, that equals to 1 squared plus 1 squared plus 0 squared. And you multiply that to v1. Then this gives you 2 to 3 minus. So 2 plus 2 over 1 plus 1 is, I guess, 4 over 2. That equals to 2 times 1, 1, 0. Or in other words, we get 0, 0, and 3. Now, we got v1 and v2, and we can check that v1 is orthogonal to v2. And this is because, well, if you take the dot product, so v1 dot v2 equals to v1 transpose times v2. That gives you, I guess, 0 plus 0 plus 0, that equals to 0. So we can iterate this idea for more number of bases. So suppose now that we have 3 vector, which is the basis for a subspace W of R4, then we can cook up an orthogonal basis by doing the same thing, but for 3 times. So basically you choose one vector in the set, say v1 equals to x1. Then you set w sub 1 equals to the span of that vector, v1. Then we can find v2 by subtracting the orthogonal projection of x2 onto w1. So it's x2 minus projection of x2 onto w1. Then this gives you an orthogonal vector v2 of v1. And now you set w sub 2 equals to span of v1 and v2. And lastly, we take v sub 3 as x3 minus, so basically we subtract projection of x3 onto w2. then this gives you an orthogonal vector v3 to the whole set v1 and v2. So if you cook up v1 and v2 and v3 in this way, then the set v1 and v2 and v3 is an orthogonal set. So in fact, it turns out that the procedure we are doing always works for more general case. So suppose that you have a basis x1 through xp for non-zero subspace w of R to the n. Then we choose v1 equals to x1, and we set w1 equals to span of v1. And you define v2 by x2 minus projection of x2 onto w1. Then this gives you an orthogonal vector to v1. So we can define w2 as span of v1 and v2. And you do the same procedure for v3. And we define w3 equals to span of v1 and v2 and v3. And lastly, v sub p is defined by, so you take away the orthogonal projection of xp to w sub p minus 1, where w sub p minus 1 is the span of vectors given by v1 through v sub p minus 1. Then v1 through vp is orthogonal basis for w, and the span of v1 through vk is the same as the span of x1 through xk, and this is because we built v1 through vk by taking the linear combination of x1 through xk's. And this procedure is called as the Gram-Schmidt process. And once you finish all this procedure, if you scale vectors to make them length equals to 1, then we construct an orthonormal basis to the given space W. So the normalized basis, like the basis of unit vectors u1 through up, is called as the orthonormal basis for the given subspace W. Okay, so let us practice Gram-Schmidt process by this example. So suppose that W has a basis of these three vectors, and we want to find an orthogonal basis v1, v2, and v3 for W. So let us pause the video and try out this problem before I give you the solution. Okay, so did you figure the answer out? So the amount of the calculation really depends on your first choice of the vector. Like if you chose the first vector as like a v1, then it's gonna get really hard. And that's because the first vector has less number of zeros. So let us choose v1 equals to, say, the second vector, 1, 2, 0, 0. So let's say this one to be x1. And then x2 to be the most similar vector to x1. So let us say the first one to be x2, and let's say the last one to be x3. Then we can set w sub 1 equals to span of v sub 1. Then v2 equals to x2 minus the projection of x2 onto the space w1. Then this gives you 1, 2, 3, 0 minus the projection, which is given by x2 dot product with v1 over v1 dot product with v1. And you multiply this with v1. Then this gives you 1, 2, 3, 0 minus x2 v1 equals to, I guess, 1 squared plus 2 squared plus 0 over the magnitude of v1 is just 1 squared plus 2 squared. And if you multiply v1, then you get 1, 2, 0, and 0. So this equals to 1, 2, 3, 0. And now we have the same numerator and the denominator. So that gives you 1, 2, 0, 0, or simply we get 0, 0, 3, and 0. It's very cool, right? And now let's let w sub 2 equals to the span of v1 and v2. then we can find V3 as x3 minus the projection of x3 onto the space W2. Then this equals to, well, x3 is given by 1001. So we get 1001 minus, and the projection is defined as x3 times v1 over v1, the product with v1. And you multiply this to v1, and then you subtract x3 times v2, and you divide by its magnitude, v2 dot product with v2, and you multiply this to vector v2. Then this equals to 1001 minus, so the dot product equals to, well, v1 is here, and v2 is here, and x3 is here. So x3 dot product with v1 equals to 1 plus 0 plus 0 plus 0, and you divide this by the magnitude of v1, which is equals to 1 squared plus 2 squared plus 0 plus 0, and you multiply this to 1, 2, 0, and 0, and you do the same thing for the other part. So x3 dot product with v2 equals to, I guess, 0 plus 0 plus 0 plus 0 over 3 squared times 0, 0, 3, and 0. But because the numerator is 0, so we get this equals to 0. So that gives you v3 equals to 1001 minus 1 over 2 squared plus 1 is, I guess, 5. And you multiply this to 1200. Or this gives you, I guess, 4/5 and negative 2/5 and 0 and 1. So if you collect all these vectors, v1, v2, and v3, so 1, 2, 0, 0, and 0, 0, 3, 0, 4/5 and negative 2/5 and 0 and 1, then this is an orthogonal basis for the given space W. Now, we can interpret the Gram-Schmidt process as factoring the matrix whose columns are our original basis. So let's suppose that A is m by n matrix with linearly independent columns. Then we can factor A into Q times R, where Q is m by n matrix whose columns form an orthonormal basis for the column space of A, and R is an m by n upper triangular invertible matrix with positive entries on the diagonal. So all the diagonal entries are bigger than 0, which means the determinant is always positive. And here I want to note that the given matrix A is m by n matrix. That means it doesn't have to be a square matrix. So I can tell this is really a powerful factorization. And from here, if you multiply Q transpose for the both sides, then we get Q transpose A equals to Q transpose times Q times R. But we know that a matrix with orthonormal columns, which is called as orthogonal matrix, has the property Q transpose times Q equals to the identity. So this gives you I times R, or this equals to R. So if you multiply Q transpose into A, then you can immediately make the given matrix into the upper triangular matrix. So using the example below, let us see how this factorization works. So we're going to find the QR factorization of this matrix. And the first step you want to do is to identify column vectors of the given matrix. So we say x1 equals to 1, 1, 0, and x2 equals to 2, 2, 3. W equals to span of x1 and x2, which is the same as the column space of A. And what we're going to do is we're going to apply the Gram-Schmidt process to find orthogonal basis v1 and v2 of the given column space of A. So basically you choose v1 equals to x1, which is given by 1, 1, 0. And you define W sub 1 equals to span of V1, then V2 equals to X2 minus the projection of X2 onto W sub 1. Then this equals to, so X2 is given by 2, 2, and 3. And the projection of X2 onto this W sub 1 is defined as X2 dot product with V1 over V1 dot product with V1, and you multiply this to V1. Then this gives you 2, 2, 3, and you subtract. So basically, X2 is given above over here, and V1 is here. So X2 dot V1 equals to 2 plus 2 plus 0, and the magnitude of V1 is given by 1 squared plus 1 squared plus 0 squared. And you multiply this into V1, that equals to 1, 1, 0. So we got 2, 2, 3 minus 4 over 2, which is given by 2. So we get 2, 2, 0. And if you subtract that vector, we get 0, 0, and 3. Okay, so we got V1 and V2 over here. Then the next step should be, so we have to find the orthonormal basis. We need to normalize the given vectors. What does this mean? Well, we're gonna divide V1 by its magnitude, and we'll set that equals to U1. And for U2, we will divide V2 by its magnitude as well. Then U1 equals to, well, V1 is given by 1, 1, 0, and its magnitude is square root of 1 squared plus 1 squared plus 0 squared, or you get 1 over square root of 2, 1, 1, 0. And for U2, well, the magnitude of V2 is given by 3, so that equals to 1/3 times 0, 0, 3, and this equals to 0, 0, and 1. Okay, so once you get U1 and U2, then we can build Q by making them as the column vectors. So Q is defined as U1 and U2. So this equals to 1 over square root of 2, 1 over square root of 2, and 0, and 0, 0, and 1. And the last step should be, so you can find R by multiplying Q transpose into A. So Q transpose times A equals to, well, we have 1 over square root of 2, 1 over square root of 2, 0, and 0, 0, 1. And I guess A was given by, so 1, 1, 0, and 2, 2, 3. So if you copy that over here, you get 1, 1, 0, 2, 2, 3. Then this gives you a 2 by 2 matrix, 1 over square root of 2 plus 1 over square root of 2, and 2 over square root of 2 plus 2 over square root of 2, and 0, and 3. And if you calculate and rationalize the answer, like 1 over square root of 2 equals to square root of 2 over 2, then we get square root of 2, 2 times square root of 2, and 0, and 3. So you can tell that R is the upper triangular matrix with positive diagonal entries. And you want to check by yourself that if you multiply Q into R, then you will restore the original matrix A.